Hello everyone, my name is Jongha Kim. Today I'm introducing our paper, TabFlash Efficient Table Understanding with Progressive Question Conditioning and Token Focusing, which proposes a new framework for efficient table understanding, which is accepted to AAAI 2026. Multimodal Large Language Models, MLLMs, are widely adopted for table image understanding tasks such as question answering. However, they overlook two important and unique characteristics of table images, which we introduce in following slides. First problem is that only a small region within a large table image is relevant to the question. Please carefully look at the table on the screen, where I'm going to give you a question. So, the question is, what is the time difference between the runners in lane 4 and lane 9? Can you correctly answer the question based on your memory without looking the table image again? To answer the question, you should focus on the yellow cells highlighted. As you may notice, the question is very hard to answer if not examining the image while also considering the question. This example demonstrates the importance of question-aware visual feature extraction, which previous MLLMs failed to provide because their vision encoders are not aware of question information. The second major issue is that a large portion of a table image is mostly redundant. Specifically, white background areas in image compose a large portion of a table image and contain no information. As you can see, highlighted in the image, these gray areas are mostly useless at all. In previous MLLMs, these backgrounds are also converted to visual tokens, which results in excessive and unnecessary computational costs, considering the quadratic complexity of LLM regarding the number of input tokens. To summarize, visual tokens generated in previous MLLMs are uninformative because they're question agnostic, and they're redundant due to a large number of empty background tokens. This results in low performance and high computational cost. As a solution, we propose the TabFlash architecture, which generates informative and compact visual tokens. This results in state-of-the-art performance with significantly less computation. To generate question-aware visual tokens, we inject question information directly into the vision encoder, vision transformers in this case. We use a question injection strategy, shown here in red, to ensure the encoder is no longer question agnostic. Instead of randomly or indiscriminately injecting the question to VIT layers, we propose progressive question conditioning, considering each layer's capacity to handle additional information. In detail, early layers of VIT are unstable, while latter layers are more stable, so we increase question conditioning frequency progressively as we move to deeper layers in the network. By following this progressive approach shown in the red box, question information is effectively injected to VIT. This ensures the resulting visual tokens are significantly more informative than those from question-agnostic models. Our second method is norm-based pruning with token focusing. We observed that the outer norm of division tokens effectively detects background tokens. Tokens with low norms typically correspond to background regions we saw earlier. As shown in the red box, we prune these lower norm tokens before being fed into the language model for efficiency. However, although the figure on the top shows that background tokens are effectively being pruned, we observe that 13.5% accuracy is still being achieved using only the pruned tokens, as reported in the table below. This results in the case that crucial information is still being stored on those pruned tokens, which results in significant information loss if we simply discard them. To concentrate this crucial information only to the retained tokens and minimize the information loss caused by the pruning, we introduce token focusing. This training method suppresses correct predictions from pruned tokens while promoting correct predictions within the retained set as shown in this red box. Combining the norm-based pruning and token focusing, we retain a compact set of visual tokens with minimal information loss. As a result, we now have tokens that are both highly informative and compact. TabFlash 3 billion achieves state-of-the-art results, outperforming both proprietary models like GPT-4o, Gemini 2.5 Pro, and top-performing MLLMs across 7 table question answering benchmarks. Regarding the efficiency, TabFlash 3 billion model achieves the best performance with 27% lower flops compared to the second best model, InternVL. Also, TabFlash 1B model demonstrates exceptionally low flops and memory usage while outperforming most baselines. Our ablation study confirms that improper conditioning can actually degrade performance, shown by lower performances than no conditioning. On the other hand, the proposed progressive strategy achieves the best results, significantly outperforming all other approaches. We also verified the impact of token focusing. Without token focusing, crucial information remains trapped in prune tokens. With token focusing, we successfully concentrate the information to retain tokens, thereby reducing prune token accuracy to 0, while further improving retained token accuracy to 48.4. TabFlash also shows superior performance on table fact verification and table-to-text generation tasks beyond question answering tasks. Qualitative results also show that TabFlash successfully allocates high attention scores to question-relevant regions. Compared to the baseline, our model focuses much more precisely on the cells needed to answer to the questions. In conclusion, we propose TabFlash, which addresses the uninformative and redundant token problem in previous MLLMs. By combining progressive question conditioning with token focusing to obtain more informative and compact set of visual tokens, we achieve state-of-the-art performance with significantly less computational cost. Thank you for listening.